Okay, good afternoon, guys. So I finished grading your homework 6, and I liked one um, choice of characters, Bert and Henry, Ernie. So yeah, this this guy, of course, would receive full grade even if you would do the rest of the work. Um, what else? In um, in our models, we sometimes write these and padding token set to the end of sentence token. So, do you know why for GPT models we should assign this padding token separately? So, like we said, um, for example, last time in our notebook here, um, let's see, notebook. Yeah, so for example, here, setting pet token ID to end of sentence token ID. So, do you know why we always see this information when we use GPT models? I kind of didn't mention that. Why GPT model dictionary doesn't have the padding token?
Use that sentence token.
Could you repeat, please?
They just use the end of sentence token as the padding token.
So do you remember we used padding token just to make all the sentences in the batch of the same size? Do we need this for GPT model? So the question is why we set padding token to end of sentence for GPT models? Yeah.
You don't necessarily care about the length of your output, and if anything, most human language has varied output lengths.
It's
So then one.
no, it's just related to how we train our GPT model. Because in GPT model, it predicts the next token. So we actually don't know the end of sentence. And if we, during generation, if we want to pad, we set padding token to the end of sentence token. So in BERT model, there is a special token for padding. In GPT model, there's. So I just wanted to uh, mention this. Okay, so today we're going to. Uh, so last time we talked about image to text. Today I want to talk about text to image task, and uh, kind of the most famous model is called Stable Diffusion and Flux. So they are using variational autoencoder and diffusion models under the hood. So today we will talk about variational autoencoder and GANs, and next time we will talk about diffusion models. So this is the plan. And because I um, couldn't share, couldn't upload my notebooks in open access, you can find these notebooks on my courses, the notebooks that I'm using today, because they're from another course on computer vision. So let's get started. And also, if you want to follow the presentation, I uploaded presentation on GitHub because there will be a lot of formulas, and maybe you want to go back, you can kind of follow the lecture and using this presentation. Okay. Okay, so what is the autoencoder model? Do you remember in just in neural networks? What is how does this model look like? What do we call by just autoencoder but without variational? So we have a neural network which kind of has smaller hidden layers than input and output layers. And this is called autoencoder. So and this part is called bottleneck. And the idea is, so we have input, you can think about image as input, and we have output, and we train this neural network to minimize the distance between X and reconstruction of X. So MSE loss to minimum. And this neural network will learn the weights, and of course you understand that if you take an arbitrary matrix of 224 pixels by 224 with arbitrary numbers, it's unlikely that you will see a picture, an image from real world. So I think we talk about this on the second lecture of our class, that the dimension of the data is much smaller than its real representation. So the idea of this autoencoder models was to kind of squeeze this information in smaller dimensions and use this as representation of our data. So you remember we began our class with PCA, principal component analysis, and dimensionality reduction, and we will finish our class with the same topic, dimensionality reduction, but in more in involved way. So, so and yeah, let's recall principal component analysis, the topic that we actually um, began our class with. So the idea was if we have, for example, two-dimensional data points, points with two coordinates, to find a one-dimensional direction, such that and project our data on this line such that the variance of the points on this line is the greatest. So this is PCA. Now let's look at the probabilistic formulation of this problem. So we have X point in multidimensional space and Z the representation in low dimensional space. And you remember there is a linear function. Mu corresponds to the center of this data, and matrix W transforms two-dimensional data into one-dimensional. In general case, the capital dimensional data into the lowercase dimensional data. But now we will assume that there is also noise. And if this noise has zero mean and variance sigma squared, then we will have the following model that our data points have this mean, the mu plus reconstruction of the latent variable, and the variance sigma squared. And they have normal distribution. I will use one letter for parameters. In this case, theta stands for all parameters mu, which is the capital dimensional vector, matrix W, which is the capital times the lowercase, and sigma. So the set of parameters. And finally, we assume that our variable z, the low dimensional variable, has the standard Gaussian distribution. Under this assumption, we can write the joint probability. As you remember, joint probability is the conditional probability times the probability of condition. And this is how the distribution, joint distribution looks like. The problem is that we don't observe latent space variables. We don't observe z. We observe only x input. That's why these models are called models with latent variables. Now let's move a little bit further, and instead of using linear assumption of our transform, we will change this mean and variance to nonlinear functions. And what is the most general nonlinear function? Neural network. So instead of mean as a matrix and variance as a number, we will use two neural, well, actually, it's one neural network, but in its output, we will have two sets of parameters. So mu has the shape D capital, and covariance matrix, we will use diagonal covariance matrix. And if it's only diagonal, then it also has only D numbers, D capital numbers. So the output shape will be 2 times D capital. So, and this model is called variational autoencoder model. Now let's talk about how to actually learn this model. So, as I said, we have access only to X variables, to the input images. But we want, let's see, but we want to estimate joint distribution, probability of X and Z. So, because we have access only to our X variables, and we can observe only input images, for example, then we will work with probability of the input x. It's called partial likelihood. And so here we just write the log likelihood, the product over all data points. And theta stands for the parameters of our neural network. And now we will do one trick. We will multiply these functions. So we have in points x1, x2, x3, and so on. And we have endpoints. By points, I mean, for example, three-dimensional images. And to each point, we want to assign a latent representation, z1, z2, and so on, zn. But we don't know the distribution of the latent variables. And let's denote this distribution by q with superscript I, which is the same. I will use two notations interchangeably as the distribution on z given point xi. But the meaning is that for every point xi, we have the latent representation z. Okay, so, and then we introduce just arbitrary distributions q. We don't know, you can use arbitrary distribution q on latent variable z and multiply our terms by 1, by the integral of q with respect to z, because the probability density function, integral of probability density is 1. And z, it depends on z, it doesn't depend on x. So we will multiply, and we didn't change anything. And then we also multiply and divide by this distribution that we don't know of the latent variables by q. And this is how our partial likelihood will look like. So next step, we will split the log of the product into sum of logs. So I will use these terms for the first term and this fraction for the second term. So I will have joint probability of x and z over q, and q over conditional probability here. And these terms, these two terms, they have special names. The last term is known as Kullback-Leibler divergence. So if you, as you remember, the definition of KL divergence is as follows: the probability times log of probability over the probability of the second distribution. And we will need only one property of this KL divergence, that it's not non-negative properties, non-negative. So yeah, you can look at the proof of this property on Wikipedia. So the second term is non-negative. And the first term, we will keep the first term. So our log likelihood will be estimated by the first term, because the last term is non-negative. So if we just remove this term, the sum will be smaller. So we have this inequality that partial likelihood is estimated by the first term. And the first term is called evidence lower boundary, ELBO, because it's lower boundary for our life. And we will actually, our goal is to estimate the distribution on latent variables, Q. So we will, but we have only our data X. So we will maximize this lower boundary, and it will also maximize the probability of the observed data. So this is the idea. Okay, some more transformations. So this is our evidence lower boundary. And as you remember, the joint probability is equal to the conditional probability times probability of condition. So yeah, so P of Z and X is equal to P of X given Z times P of Z. So I split the first term. So the first term is equal to P of X given Z times P of Z. I split into, again, a sum of logarithms. If you look at the second term, if we flip this fraction and we'll have Q on the top, it will be Kyle divergence. So to flip the fraction, I use power -1, and it goes as minus from logarithm. So this is the second term, Kyle divergence between distribution on our latent variables and our prior, just uniform, standard normal distribution. The first term has its own name. The first term is called the reconstruction error, because we have X here conditioned on the latent variable Z. So we kind of have the neural network Z, and in the output we have X give, but conditioned on Z. And in the input we have X unconditioned. Actually, we have in the output just parameters of our distribution U and diagonal matrix sigma. But if we know the parameters, then we know the distribution. So if you think about this probability as normal distribution, then log of exponent, normal distribution has formula. You remember the 1 over square root of 2 pi power d times determinant of matrix sigma e power negative, and so in this case it will be x, the reconstruction of x minus mu sigma inverse the reconstruction of x minus mu and 1/2. So if we take a log of this expression, you will get MSE loss. And that's why, so this term will be just the MSE loss. So that's why it's called reconstruction. The error between x given z and true x. Okay, now we want to learn Q. And now we need to make some assumptions. And our assumption will be that we will use the so-called factorized Gaussian family. Factorized Gaussian family distribution means that the instead of this expression, we will have the product of one-dimensional exponents. First component squares times 1 over 2 lambda to second component squared, and so on. So it's equivalent to the previous expression when our matrix is just diagonal. Do you agree with that? That if we have all zeros here, then we will multiply our parentheses just by one number, by lambda squared here. The second coordinate will be multiplied by the second, and as the result, it can be represented as a product. So that's why it's called factorized. So we don't have what's called correlation coefficients. Okay, so and for every point xi, we will introduce its own mean and its own matrix lambda. So the second term, if our distributions are normal distributions, has explicit formula. So the second term has explicit formula for this mean and lambda. So the first term doesn't have the explicit form. Okay, so for now, our model looks as follows. We have input image X. We somehow introduce this distribution Q that is normal, and it has parameters mean and covariance metrics. And so we denote this distribution by Q of Z given X. And if we learn these parameters, we can sample from this distribution a latent representation Z. Again, assume that we can learn these parameters, then we have the normal distribution and we can sample Z variable. Then we can pass the Z variable to our neural network. Our neural network will return mean and variance, but of the size of our original data. And then we can sample from the distribution for original data. And it means that we can sample an image, generate a new image. But if we have thousands of images, it means that we should learn 2,000 of these parameters times dimension. And if we have a new image, we actually won't have these parameters at all. So the second idea is to substitute these parameters with another neural network. So it's called amortized inference. And I will denote the parameters of the second neural network by. So this neural network will take an image and will split two numbers, two vectors, because it's low dimensional representation, mean and diagonal covariance matrix. And this is the entire model of the variational autoencoder. We have two neural networks. One is called encoder. The second is called generator, because second generates images. And now actually we can have this representation for arbitrary input x. We are not limited only by our training data. And now the question is how to train these neural networks, because the model looks good, but we don't know how to train these parameters. Okay, so our evidence law boundary looks as follows, but now instead of just Q, I will use Q with subscript phi that corresponds to our encoder weights. And this generator has parameters theta and L divergence. We will use stochastic gradient descent. So instead of the sum over all points, we can use just one point. So we rid of the sum. This is called stochastic gradient. And to get the unbiased estimator, we should also multiply by n, because as you remember, in stochastic gradient descent in loss function, we have 1 over n here. If we don't have 1 over n, we should multiply by n. So there is no problem with the second term, because we have the explicit expression for the second term for the Kleiner divergence. But now we want to estimate these integrals. Yeah, and when we take derivative with respect to generator, the second term doesn't depend on theta, so I didn't write this second term. So, do you know, well, David knows, but does anyone know how to estimate multidimensional integrals? It's called Monte Carlo estimation. So if we have, for example, I will provide example in one-dimensional case just to give an idea, integral between 0, 1, and you can use from a to b of a function x. We can use batch estimation. For example, if we use batch of size m, so we sample m points from uniform distribution and just take the average of this of our function calculated at these points. So it follows from the law of large numbers. You remember maybe the law of large numbers says that if we have the sum of m random variables, maybe I can use n, then it converges to, if they are sampled from the same distribution, to the mean. And the mean is the expected value of the random variable, and the expected value is the integral of the PDF probability density function times x, but we can use also function here of x. And if our PDF is uniform, it will be just 1. and you will get the integral. So this is a well-known fact from probability theory. And it was introduced in 60s to evaluate, to calculate the some equations for a nuclear bomb, and they called this Monte Carlo method because of the casino in Monte Carlo, because we use probabilistic approach. So, okay, let's try to apply Monte Carlo to estimate the integral. And we can do that here because our function, the first function, depends on both and z and x. And the function here also depends on z and x. To avoid this problem, we should use the last trick, which is called reparameterization trick. So you remember that our variable z had a normal distribution with parameters m and lambda. So we can represent arbitrary normal uh, normally distributed variable through the standard normal variable. So here I'm using epsilon, which has a standard normal distribution. And if you calculate the mean of this sum, the mean of epsilon is 0, you will get the mean m. If you want to calculate the covariance matrix of epsilon is 1, identity matrix, and you will get lambda. So this is just the representation of arbitrary Gaussian variable through the standard Gaussian variable. But in our PyTorch code, we can't just sample a random number and take derivative with respect to this number. Now you can sample a standard normal variables and take the derivative with respect to parameters of your neural network, because this m and lambda no longer sampled numbers. Only epsilon was sampled. So this is called reparameterization trick. And also, if we use this substitution here, then x minus mean will result in just epsilon times covariance matrix. And here we have inverse covariance matrix. They will cancel out, and we will get the standard normal distribution. So instead of this normal distribution, we will have standard normal distribution. And standard normal distribution now doesn't depend on z. It doesn't depend on z. And now we can apply Monte Carlo estimation. And in Monte Carlo estimation, we sample epsilon. So we sample epsilon from normal distribution. And in machine learning, we typically use just one, m equals to one sample. So for mini-batch estimation, I should write 1 over m and sum over for m samples from standard normal distribution. But if m is 1, we will get just one sample. And that's it. So now we have it's called doubly stochastic inference, because we apply approximation first for stochastic gradient descent, we use one sample. And then we also apply mini-batch estimation for the integral. And again, use just one sample. So it's called, you can hear this double stochastic inference. Okay, and now when we represent these distributions by neural networks, we can just calculate autograd from these neural networks. And we will see this in code. And finally, we can, when we train our neural networks with stochastic gradients, we can sample new images. To sample new images, you just sample a random point with standard normal Gaussian distribution, pass through generator. Generator splits mu and sigma, and then you sample the Gaussian a variable from Gaussian distribution with these parameters mu and sigma. Now, let's see if it's my last slide. Let's look at the code examples, which is more fun than theory. So, and again, this code is on my courses. I can't upload this on GitHub. So we use Scilab. Oh, I didn't translate this. So in the first part, we train just simple autoencoder, just a neural network with two, you can see with, oh no, we use here ResNet as encoder. And here are the results. The input images and reconstructed images. So you can see that they look a little bit similar, a little bit blurry. So autoencoder actually does its work as like reconstruction of the images. We can also look at the latent space, and you can see that latent space in standard autoencoder has the property of continuity, so continuous transformation from one image to another. How to generate images without encoders? This is the problem. So in this example, we just calculated mean and covariance matrices for all the images and tried to sample from normal distribution with these parameters. So these are results. Uh, so because in this data set faces were centered, when we calculate mean, it will be common for all the faces. So you can see that faces look not bad, but the background is not realistic. And of course, the problem with these images is our assumption that latent space had normal distribution. In variational encoder, we force our images, we force our latent space to have normal distribution, because you remember there was, let's see if I have formulas, there was Kyle divergence between our latent distribution Q of z given x and standard normal distribution. So we force our model actually to learn normally distributed latent representations. So this is the neural network. So um, we have our ResNet part, and then we apply two linear layers uh, corresponding to mu and sigma matrices. Um, and let's look at the results. So, so this is the reconstruction. You can see that um, reconstruction um, well, it was trained just for 4 or 5 epochs. So, but in general, variable autoencoder has these blurry reconstruction images. Uh, if you look at the latent space Z, so we just take two arbitrary image, apply encoder, we have vector representation Z, and then we can interpolate between Z. Looks also continuous. And the generation of new images. Now, the background doesn't look like in the previous example for autoencoder, not realistic. And we have diverse faces and a little bit blurry. And now let's look at the guns. Um, I didn't talk about guns. Ah, so this is just to give you an idea. All these 6 images, they have the same MSE loss because we trained reconstruction loss and it was MSE loss. Um, just to give you an idea why the model learns blurry images, because if you compare these images, they will have the same reconstruction loss. So here just pepper noise. Uh, it's just blurry, and this is just JPEG. And these images, there's just a different contrast, which resulted in higher MSE loss, even though images are similar. And this image was just shifted by 3 pixels, which resulted also in higher MSE loss. And I'm not going to talk about GANs, I just will show the results. So if we use generative adversarial networks, the images look much sharper, but less maybe realistic. But it's in just because it wasn't trained enough. The main problem with generated images with GANs is that you can see the same face everywhere. So this is the difference between these two models. The variational autoencoder generates diverse images, but not very sharp quality. GANs, they are trained using discriminator, which actually detects if the image is blurry or not. So they have good quality, but they suffer from so-called mode collapse when images are generated from the same mode of our distribution. And this is the interpolation. I don't know why there's image of a dog. So, mm, you can see that GANs also don't have the linear interpolation because property. In some cases, there's contrast between like nearby images. Okay, we should stop here for today. And next time we will talk about diffusion models, which actually fix these problems. And also, you can look at the VAE GAN when people add discriminator to variational autoencoder, which also may forces the images to have high quality. Okay, so let's stop here for today.